There's something hauntingly beautiful about the night sky, a vast, endless canvas dotted with stars, planets, and galaxies, each holding secrets we've only begun to unravel. But what if I told you that some of these cosmic wonders don't just defy explanation, they shatter everything we thought we knew about the universe? Picture this. You're staring up at the stars when suddenly a pulse of light flickers where nothing should exist, or a distant galaxy spins in a way that physics says is impossible. These aren't scenes from science fiction. They're real, documented events that have left even the most brilliant astronomers utterly stumped. Welcome to a journey through 29 of the most bewildering mysteries in space and time. Phenomena so strange, they've sparked debates, rewritten textbooks, and made scientists question the very fabric of reality. From eerie radio signals repeating like cosmic Morse code to black holes that seem to break the rules of gravity, each of these enigmas is a puzzle waiting to be solved. What causes a star to vanish without a trace? How can time itself appear to warp in ways Einstein never predicted? The answers, or lack thereof, will leave you questioning everything you thought you knew about the cosmos. This isn't just a list of oddities, it's an invitation to step into the unknown, to explore the edges of human understanding where science meets the inexplicable. By the time we're done, you'll see the universe not as a static backdrop, but as a dynamic, ever-changing mystery, full of questions that beckon us to look deeper. So, are you ready to confront the enigmas that defy logic and challenge the limits of our knowledge? Let's dive into the abyss together, because the truth is out there, and it's far stranger than we've ever imagined. In the summer of 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something that would send shockwaves through the scientific community. For 72 seconds, a narrowband signal blasted through the void, so intense, so precise, that the astronomer who discovered it, Jerry Amon, circled the data on his printout and scribbled a single word in the margin: "Wow." That burst of energy, radiating at a frequency close to the hydrogen line, a band many scientists believe extraterrestrial civilizations might use for communication, was unlike anything ever detected before or since. It wasn't static or interference. It wasn't a passing satellite or a stray cosmic event. It was a clean, focused scream from the depths of space, originating near the constellation Sagittarius, and then silence. No repeat, no echo, no explanation. What made the wow signal so baffling wasn't just its strength or its unnatural frequency. It was the way it behaved. Natural cosmic phenomena don't transmit in such a narrow band. They're messy, scattered. This was surgical, as if someone had tuned a cosmic radio to a specific channel. And then there's the duration, 72 seconds exactly, matching the telescope's fixed observation window. Was that a coincidence, or was something or someone aware it was being listened to? For decades, astronomers have chased answers. Maybe it was a comet's hydrogen cloud, as one controversial theory suggested, except no known comet was in the area at the time. Maybe it was a rogue military transmission or a satellite glitch, but no human technology matched the signal's profile. And if it was extraterrestrial, why hasn't it happened again? SETI, the search for extraterrestrial intelligence, has scanned the same patch of sky countless times since, ears straining for another whisper. Nothing. The wow signal lingers like a cosmic ghost, a single note in an otherwise silent universe. It forces us to confront the unsettling possibility that we might have heard a voice just once and missed our chance to reply. Or worse, that the universe is playing a joke on us, dangling the tantalizing hint of contact before snatching it away. Either way, it remains one of astronomy's most tantalizing what-ifs, a mystery written in 72 seconds of data and a single, awestruck word scrawled in red ink. Imagine the universe as a vast ocean with galaxies drifting like ships on gentle currents. Now picture those ships suddenly changing course, all moving in the same direction against the tide, not randomly, but as if pulled by some unseen anchor in the distance. That's the eerie reality astronomers face with dark flow, one of cosmology's most perplexing mysteries. In 2008, a team analyzing data from NASA's Wilkinson microwave anisotropy probe made a startling discovery. Hundreds of galaxy clusters, each containing thousands of galaxies, were streaming toward a single point in space at nearly 2 million miles per hour. This wasn't just gravity at work. The sheer scale and uniformity of the motion defied all known laws. The Milky Way and Andromeda might tug at each other, but this was different. Entire swaths of the cosmos, separated by billions of light years, were marching in lockstep toward something outside our observable universe. Theories swirl like cosmic dust. Some suggest the pull comes from a supermassive structure beyond our cosmic horizon, perhaps a gargantuan cluster of matter so dense it warps space-time itself. Others propose even wilder ideas, a neighboring universe brushing against ours in the multiverse, its gravity leaking through like footsteps in the next room. Then there's the unsettling possibility that Einstein's equations might need rewriting. That dark flow hints at forces we've yet to imagine. But here's what makes dark flow truly unsettling. If something is out there, we may never see it. The observable universe is like a bubble limited by the speed of light. Beyond it, the cosmos expands faster than light can reach us. Whatever's tugging these galaxies could be forever hidden, a ghostly hand guiding the universe from the shadows. Every new observation deepens the mystery. In 2013, the Planck satellite's data seemed to confirm the flow. Then later studies questioned its significance. The debate rages on, a reminder that even our most advanced tools can't yet pierce the veil of the unknown. Dark flow doesn't just challenge our maps of the cosmos. It whispers that the universe might be stranger, vaster, and more interconnected than we ever dreamed. The universe is unimaginably vast, a sprawling expanse of hundreds of billions of galaxies, each with hundreds of billions of stars, many of which likely host planets in the so-called Goldilocks zone where life could thrive. Given those staggering numbers, it seems statistically inevitable that we should have company out there. And yet, when we listen, when we search, when we scour the cosmos for any hint of another civilization, all we hear is silence. This glaring contradiction between the overwhelming probability of alien life and the utter lack of evidence for it is known as the Fermi Paradox, and it's one of the most profound mysteries in science. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunchtime conversation in 1950, the paradox cuts to the heart of our cosmic loneliness. The math suggests that even if intelligent life is exceedingly rare, the sheer scale of the universe should have produced countless civilizations by now, some of which should have spread across the galaxy, leaving unmistakable traces. So why haven't we found them? The silence isn't just puzzling, it's unsettling, forcing us to consider possibilities that range from the sobering to the downright chilling. One explanation is the Great Filter hypothesis, the idea that some catastrophic barrier prevents civilizations from reaching interstellar maturity. Maybe life is common, but intelligence is a fluke snuffed out by evolution's randomness. Or perhaps advanced societies inevitably destroy themselves, whether through war, environmental collapse, or reckless technology. If that's true, the filter could lie ahead of us, a looming existential trap we haven't yet encountered. Alternatively, we might be the first, a rare spark in a universe still waking up to the possibility of consciousness. Then there's the darker side of the paradox. What if the silence isn't accidental but intentional? Some theorists suggest advanced civilizations might be deliberately avoiding us either out of caution, indifference, or something more ominous. Imagine a universe where predatory alien societies lurk in the shadows, forcing others into radio silence to avoid detection. Or consider the possibility that we're simply too primitive to notice the signals all around us, like ants unaware of a bustling city just beyond their colony. Yet another angle is that we're looking in the wrong way. Our searches focus on radio waves and visible light, but what if advanced civilizations communicate through neutrino beams, quantum entanglement, or other technologies we can't yet comprehend? The universe could be buzzing with conversations we're too primitive to hear. The Fermi Paradox doesn't just challenge our assumptions about life, it forces us to confront the fragility of our own existence. Every unanswered signal, every empty patch of sky is a reminder that the universe doesn't owe us answers. It's possible we're alone. It's possible we're not. But until we know for sure, the question hangs over us like a cosmic riddle, whispering that the truth, whatever it is, might change everything. Somewhere in the vast darkness between galaxies, a cosmic alarm clock goes off just for a millisecond. In that fleeting instant, a burst of radio waves erupts with the power of 500 million suns, then vanishes without warning. This isn't a one-time fluke. Since their discovery in 2007, fast radio bursts have baffled astronomers with their sheer intensity and eerie unpredictability. The universe seems to be flickering, sending out these blindingly bright signals from billions of light years away, and we still don't know why. What makes FRBs so mystifying isn't just their energy, it's their variety. Some are one-off explosions, like cosmic firecrackers that disappear before we can pinpoint their origin. Others, like FRB 1211-2, repeat in erratic patterns, pulsing again and again from the same patch of sky. The repeating bursts are particularly tantalizing. Natural cosmic events, supernova, black hole collisions, don't typically rewind and replay. So what could possibly be causing these encores? Theories abound, each more fascinating than the last. One leading idea points to magnetars, ultra-dense neutron stars with magnetic fields so strong they could strip the electrons from your atoms at 1,000 kilometers away. When these stellar corpses undergo starquakes, massive fractures in their crusts, they might unleash the energy equivalent of a stellar scream, rippling across the cosmos as an FRB. Then there's the possibility of cosmic cataclysms, colliding neutron stars, evaporating black holes, or even the violent birth of new physics we haven't yet discovered. But of course, there's the elephant in the room. Could these be artificial? The precision and power of FRBs have led some to speculate about alien megastructures or interstellar beacons. Imagine a civilization harnessing the energy of stars to send targeted pulses across galaxies, a cosmic Morse code meant to announce their presence. It's a long shot, but the universe has surprised us before. The real challenge lies in catching these bursts in the act. FRBs are so brief that by the time telescopes swing toward them, they're often gone. New arrays like CHIME in Canada are changing the game, scanning huge swaths of sky daily and cataloging hundreds of these elusive signals. With each new detection, patterns emerge. Some FRBs arrive with a telltale swoosh of scattered frequencies, hinting at turbulent plasma clouds they've passed through. Others seem eerily clean, as if engineered to cut through cosmic noise. Perhaps the most haunting question isn't what causes FRBs, but what their existence tells us about the universe. If these bursts are natural, they point to astrophysical processes far more extreme than anything in our textbooks. If they're not, well, that's a conversation humanity might not be ready to have. Either way, every new burst is a reminder the cosmos is far from silent. It's shouting at us in a language we're only beginning to decipher. For decades, NASA Pioneer 10 and 11 spacecraft sailed through the solar system like cosmic postcards, carrying messages from humanity into the void. But by the 1990s, something strange emerged from their day. Both probes were slowing down ever so slightly, as if space itself had a hidden drag. Calculations showed they were decelerating at a rate of about 300 billionths of a meter per second squared, a tiny but undeniable deviation from the expected trajectory. This wasn't a measurement error or a gust of solar wind. It was a persistent, nagging anomaly that defied every known force in physics. At first, scientists assumed mundane explanations, maybe gas leaks from the probe's thrusters or thermal radiation pushing unevenly against their surfaces. But after painstaking analysis, none of these held up. Pioneer 10 and 11 were identical in design, yet both exhibited the same unexplained slowdown across billions of miles. Even more bizarre, the effect seemed constant, as if some unseen hand were gently applying the brakes, regardless of how far the probes traveled from the Sun. The implications were staggering. If this wasn't an engineering quirk, it hinted at a gap in our understanding of gravity itself. Some theorists proposed exotic possibilities: dark matter's gravitational tug, modifications to Einstein's theory of relativity, or even the influence of higher dimensions warping spacetime in ways we can't yet measure. Others wondered if the anomaly pointed to something far more profound, a shadowy, uncharted force acting on all matter in the cosmos, one that only becomes noticeable in the vast emptiness between planets. Then, in 2012, a team of researchers cracked part of the mystery. Meticulously reconstructing the probe's heat signatures, they realized thermal radiation from their power systems was emitting asymmetrically, creating a tiny but consistent push, like a car's exhaust pipe blowing unevenly and nudging the vehicle off course. Case closed, not quite. While this explained most of the deceleration, some measurements still didn't align perfectly, leaving room for lingering questions. The Pioneer Anomaly stands as a humbling reminder that even our most precise instruments can reveal gaps in our knowledge. It's a testament to the scientific process, decades of scrutiny, wrong turns, and incremental progress, but also to the universe's stubborn refusal to fit neatly into our models. Perhaps the greatest lesson isn't about the anomaly itself, but about the mysteries still lurking in the data we've yet to decipher. After all, if something as subtle as heat radiation could confound us for years, what else might we be missing in the quiet depths of space? In the constellation Cygnus, 1,200 light-years from Earth, a star named KSE 8462852, better known as Tabby's star, behaves like nothing else in the cosmos. Most stars flicker gently, their light dimming by fractions of a percent as planets pass in front of them. But Tabby's star doesn't play by those rules. It plunges into darkness erratically, sometimes dropping a staggering 22% of its brightness for days or even weeks at a time. That's not a gentle shadow, it's like someone flipping a cosmic dimmer switch, blotting out a fifth of the sun in our own solar system. And no one knows why. When astronomer Tabetha Boyajian first spotted these bizarre dips in data from NASA's Kepler Space Telescope in 2015, the explanations ran the gamut from mundane to mind-bending. Could it be a colossal swarm of comets breaking apart and casting thick shrouds of dust across the star? Maybe, but the sheer scale required would be unprecedented, like 1,000 Halley's comets disintegrating in perfect unison. Others proposed a newborn planet still shrouded in debris, or even a warped protoplanetary disk tilted at just the right angle to block the star's light in unpredictable ways. Yet none of these theories fully account for the star's most baffling trait, its long-term dimming. Over the past century, archival data shows Tabby's star has faded by nearly 15% overall, as if something is slowly draining its light year after year. Then, of course, there's the elephant in the room, the idea that sent shockwaves through the scientific community when it was first floated. Could these unnatural light patterns be evidence of alien engineering? In 1960, physicist Freeman Dyson theorized that advanced civilizations might build vast energy-harvesting structures around stars, known as Dyson swarms. These hypothetical megastructures made up of orbiting solar panels or habitats would block starlight in irregular, geometric ways, much like the dips observed at Tabby's star. It's a tantalizing thought, but also a cautionary one. Science thrives on evidence, not speculation, and extraordinary claims demand extraordinary proof. The truth is, Tabby's star has defied every attempt to pin it down. When astronomers trained radio telescopes on it, listening for the telltale hum of alien technology, they heard only silence. Spectroscopic studies revealed no excess infrared heat, the signature you'd expect from a dust cloud absorbing starlight. Yet the dimming persisted. Even more perplexing, some of the star's dips appear symmetrical, almost artificial in their precision, while others are jagged and chaotic, as if nature itself can't decide what's happening. What makes this mystery so compelling isn't just the star's odd behavior, it's what it represents. Tabby's star forces us to confront the limits of our knowledge, to admit that even in an age of space telescopes and supercomputers, the universe can still throw us a curveball. Whether the answer lies in undiscovered astrophysics or something even more profound, one thing is certain: this star refuses to be ignored. It's a cosmic riddle written in shadows, daring us to look closer, to question deeper, and to wonder, what else might be lurking in the dark? Picture the Milky Way not as a static island in space, but as a ship caught in a relentless current, pulled toward something unseen with terrifying force. This isn't science fiction, it's the reality of the Great Attractor, a gravitational behemoth lurking in the cosmic shadows, dragging entire galaxies toward it at speeds exceeding 1 million miles per hour. And here's the chilling part: we can't even see what's doing the pulling. The story begins in the 1970s, when astronomers mapping the motion of galaxies noticed something odd. The Milky Way, along with its neighboring galaxies in the local group, wasn't just drifting aimlessly, it was racing toward a specific point in space near the constellations Centaurus and Hydra. But when they looked in that direction, they found nothing capable of explaining such a colossal tug. The culprit lay hidden behind the Milky Way's own galactic plane, a region so dense with stars, gas, and dust that telescopes struggle to pierce through. It's like trying to spot a lighthouse through a blizzard. We know it's there, but the storm obscures everything. What little we've glimpsed only deepens the mystery. The Great Attractor isn't just a single massive object, it's a sprawling web of galaxy clusters, each with trillions of stars, centered on a supercluster called Laniakea. Yet even Laniakea's immense gravity can't fully account for the observed motion. There must be something more, something beyond our current vision, exerting an even greater pull. Some theorists speculate about dark flow, the same mysterious force dragging distant galaxy clusters acting on a local scale. Others wonder if the Great Attractor is merely a waypoint, a stepping stone toward something even larger lurking in the void. The most unsettling possibility: we might never know the full truth. The Milky Way's dusty disk blocks nearly 20% of our view, creating a celestial blind spot astronomers call the zone of avoidance. Even advanced X-ray and infrared telescopes can only tease out hints of structure galaxies warped by gravity, strange radio emissions, the faint glow of hidden stars. It's like hearing the roar of a waterfall just beyond a thick fog. You know something powerful waits ahead, but its true nature stays maddeningly out of reach. What's clear is this: the great attractor defies our cosmic arrogance. In an era where we've mapped the afterglow of the Big Bang and photographed black holes, a fundamental force in our own galactic neighborhood remains shrouded in mystery. It's a reminder that the universe still holds secrets too vast, too hidden, for even our most brilliant minds to uncover, at least for now. Every galaxy caught in its pull is a silent witness to a puzzle we've only begun to piece together. And as the Milky Way hurtles forward, one question lingers: what waits for us in the dark? Imagine two coins flipped simultaneously on opposite sides of the universe, except every time one lands heads up, the other instantly lands tails up, no matter how far apart they are. This isn't a magic trick, it's quantum entanglement, one of the most mind-bending phenomena in physics. At the subatomic level, particles can become inextricably linked, sharing a connection so profound that changing the state of one immediately affects its partner, even if they're separated by billions of light years. Einstein famously dismissed this as spooky action at a distance, refusing to believe the universe could operate in such a bizarre, seemingly impossible way. Yet decades of experiments have proven him wrong. Reality is far stranger than even he imagined. The implications are staggering. According to Einstein's theory of relativity, nothing can travel faster than light. But entangled particles appear to communicate instantaneously, as if the universe has a hidden switchboard bypassing the speed limit entirely. In 2015, researchers at Delft University conducted a landmark experiment, entangling electrons over 1.3 kilometers apart and confirming the effect with near-perfect precision. No hidden signals, no delays, just an eerie, instantaneous correlation that defies classical physics. So how does it work? The truth is, we don't fully know. One interpretation suggests entangled particles aren't truly separate but remain part of a single quantum system, their fates intertwined across space and time. Another theory posits that the particles exist in multiple states simultaneously until measured, collapsing into complementary outcomes like cosmic mirror images. Then there's the radical idea that entanglement hints at a deeper layer of reality, a holographic universe where distance is an illusion and everything is fundamentally connected. The real mystery isn't just the how, but the why. Could this phenomenon underpin the fabric of space-time itself? Some physicists speculate that entanglement might weave the cosmic web, creating the invisible threads that bind matter and energy across the cosmos. Others dream of quantum networks, unhackable communication systems leveraging entanglement to transmit information faster than light. Yet for all its potential, entanglement remains deeply unsettling. It forces us to confront the possibility that reality isn't local, that the universe operates on rules far beyond our everyday intuition. Every experiment peels back another layer, revealing a cosmos more interconnected, more mysterious than we ever dared to believe. And perhaps that's the greatest lesson of all. The universe doesn't just tolerate paradox, it thrives on it. The cosmic microwave background, the faint afterglow of the Big Bang, should be the ultimate proof of cosmic fairness. According to the foundational principle of isotropy, the universe ought to look the same in every direction, no matter where you're standing. But in 2005, data from NASA, a Wilkinson microwave anisotropy probe, revealed something that sent chills down the spines of cosmologists. The universe might have a preferred direction. Dubbed the axis of evil, this bizarre alignment in the CMB's temperature fluctuations points to a cosmic structure that shouldn't exist, one that defies everything we thought we knew about the birth and evolution of the cosmos. At first glance, the CMB appears as a near-uniform sea of microwaves, a snapshot of the universe just 380,000 years after the Big Bang. Tiny temperature variations, hotter and cooler patches no larger than 1/100th of a degree reveal the seeds of future galaxies. But when scientists mapped these fluctuations, they found an unsettling pattern. Instead of being randomly scattered, these patches seem to align along a specific axis, as if the universe had once spun like a top, leaving behind a ghostly fingerprint. The odds of this happening by chance, less than 1 in 10,000. The implications are staggering. If the axis of evil is real, it challenges the cornerstone of modern cosmology, the cosmological principle, which states that the universe is homogeneous and isotropic on large scales. A preferred direction suggests something fundamental is missing from our models, perhaps an asymmetry in the early universe's expansion, or the gravitational tug of a neighboring universe beyond our own. Some theorists have even proposed that the axis could be a relic of pre-Big Bang physics, a cosmic bruise left by whatever came before space-time as we know it. Then there's the eerie coincidence. The axis of evil aligns roughly with the plane of our solar system, an alignment so improbable it feels almost like a cosmic prank. Could this be a fluke of measurement, some subtle bias in how we observe the CMB? Or does it hint that we're somehow special, a notion that runs counter to centuries of scientific humility? The debate rages on, with some researchers dismissing the axis as statistical noise, while others argue it's the first crack in our understanding of the universe's architecture. What makes the axis of evil so unnerving isn't just its existence, it's the way it refuses to go away. Later observations by the Planck satellite confirmed the anomaly, albeit with less intensity, leaving scientists torn between skepticism and awe. If the axis is real, it could rewrite cosmology, forcing us to reconsider everything from dark energy to the multiverse. And if it isn't, well, that's almost as troubling, because it means our most precise instruments are still missing something fundamental about the cosmos. Either way, the axis of evil stands as a humbling reminder. The universe owes us no symmetry, no simplicity, no easy answers. It's a puzzle wrapped in the oldest light there is, daring us to look deeper and question everything we think we know. High above Earth, hidden in the endless blackness of space, something has been watching us for centuries at least. That's what conspiracy theorists claim. Meet the Black Knight satellite, a shadowy object allegedly orbiting our planet for 13,000 years, its origins shrouded in myth and mystery. The story begins in the late 19th century, when inventor Nikola Tesla claimed to have intercepted strange radio signals, repeating pulses he believed were coming from beyond Earth. Decades later, in the 1950s, both American and Soviet space programs reported tracking an unidentified object in polar orbit, something that shouldn't have existed at the dawn of the space age. The legend truly took flight in 1960 when Time magazine published an article about the U.S. Navy detecting a dark, tumbling object in orbit, a black knight silently circling Earth. Amateur radio operators soon joined the frenzy, sharing stories of odd transmissions, some even claiming to have decoded messages from the satellite. The most tantalizing detail, supposedly, this object predates human spaceflight by millennia, with some pointing to ancient astronaut theories, suggesting extraterrestrials left it behind as a cosmic surveillance device. But here's where things get murky. Skeptics argue the Black Knight is nothing more than space debris, a thermal blanket lost during a shuttle mission, or perhaps a discarded piece of a defunct satellite. In 1998, astronauts on the space shuttle Endeavour photographed an object later identified as a lost thermal cover, fueling the dismissal. Even Tesla's alien signals could have been natural radio pulsations from stars or Earth's own ionosphere. Yet the mystery lingers. Why? Because the black night taps into something deeper than just UFO lore. It's a symbol of our fascination with the idea that we're not alone, that some intelligence, ancient or alien, might have beaten us to the stars. Every grainy photo, every unexplained radar blip becomes a Rorschach test for our hopes and fears about the cosmos. The truth is likely mundane, but the allure of the black night isn't about evidence, it's about possibility. In a universe as vast as ours, where galaxies number in the billions, the idea that Earth might have been noticed long before we looked up isn't just fantasy. It's a reminder that the sky has always been a mirror, reflecting back whatever we're brave enough or afraid enough to imagine. The laws of physics are supposed to be unbreakable until someone comes along and bends them. That's the story of the M-Drive, an experimental propulsion system that sent shockwaves through the scientific community by claiming to do the impossible: generate thrust without expelling any propellant. According to Newton's third law, every action must have an equal and opposite reaction. Rockets push exhaust backward to move forward. That's the fundamental rule. But the M-Drive, first proposed by British engineer Roger Scheuer in the early 2000s, seemed to laugh in the face of this principle. Just a hollow, cone-shaped chamber pumped full of microwaves, it allegedly produced a tiny but measurable thrust, enough to propel a spacecraft without fuel. At first, the idea was dismissed as nonsense, a textbook example of perpetual motion fantasy. Then, in 2016, NASA EagleWorks Lab, a team specializing in fringe propulsion concepts, ran their own tests. Against all expectations, their results hinted that the M-Drive might actually work. The numbers were minuscule, just a few micronewtons of force, but if real, the implications were staggering. A spacecraft equipped with such an engine could theoretically accelerate indefinitely, reaching distant stars without the need for massive fuel reserves. No more rockets, no more limits, but here's where things get messy. Every follow-up experiment seemed to raise more questions than answers. Some teams replicated the effect, others found nothing. Critics pointed to subtle errors: thermal expansion, magnetic interference, even the faint push of Earth's own magnetic field. The M-Drive's thrust was so tiny that it danced on the edge of detectability, making it nearly impossible to rule out experimental noise. Then came the real blow. In 2021, a team at Dresden University conducted the most precise test yet, using an ultra-sensitive torsion balance. Their conclusion: the thrust was likely an illusion caused by thermal effects warping the device itself. Yet the M-Drive refuses to die. Why? Because it taps into humanity's deepest yearning, the dream of breaking free from the chains of physics. Imagine a universe where we could glide between planets on sunlight alone, where interstellar travel wasn't just possible but practical. That vision is intoxicating, and it's why researchers still tinker with variations, hunting for some overlooked quirk that might salvage the idea. The truth is, the M-Drive is more than just an engineering puzzle. It's a litmus test for how science confronts the extraordinary. Do we dismiss the impossible out of hand, or do we dare to probe the edges of our understanding, even when it leads to dead ends? For now, the M-Drive remains in limbo, a cautionary tale about measurement errors and wishful thinking, but also a beacon for those who believe the next great leap might lie just beyond the rules we think we know. Imagine carving a sphere out of the universe so vast it could hold 10,000 Milky Ways side by side, and finding nothing inside: no galaxies, no stars. Not even the faint glow of distant gas, just an eerie, perfect emptiness stretching over 1 billion light years. This isn't science fiction. It's the Boötes Void, one of the largest and most baffling structures ever discovered in the cosmos. Discovered in the 1980s during galaxy surveys, the Boötes Void defies everything we know about how the universe arranges itself. On large scales, matter should be distributed roughly evenly, like foam in a bubble bath. Clusters here, gaps there, but nothing this extreme. The void is so staggeringly empty that astronomers initially thought it was an error. Yet repeated observations confirmed the impossible. A region of space where galaxies are almost entirely absent, a cosmic desert on a scale that shouldn't exist. What makes the Boötes Void so unsettling isn't just its size, it's the way it mocks our theories. According to models of galaxy formation, even the emptiest corners of the universe should host at least a few thousand galaxies. But the Boötes Void contains fewer than 60, scattered like lone travelers in an endless wasteland. How could such a place form? One leading theory suggests smaller voids merged over billions of years, like soap bubbles coalescing into one gigantic emptiness. Another proposes a mind-bending idea, that the void is the imprint of an ancient collision between our universe and another bubble of space-time in the multiverse, leaving behind a scar of nothingness. Then there's the eerie silence. In 2013, astronomers aimed the Green Bank telescope at the void, listening for hypothetical, orphaned galaxies, ones so faint they'd been missed. Instead, they found only whispers. The handful of galaxies that do exist in the void are peculiar, often isolated and strangely quiet, as if the void itself stifles star formation. It's as though this patch of the universe forgot how to make galaxies or something, or someone cleared them out. The Boötes Void forces us to confront uncomfortable truths about the cosmos. Maybe our models of galaxy formation are missing a crucial piece. Maybe the universe is far less predictable than we thought. Or perhaps, as some theorists speculate, the void is a statistical fluke, a freak accident in an otherwise orderly cosmos. But in a universe where randomness rarely scales to 1 billion light-years, that explanation feels as hollow as the void itself. What's clear is this: the Boötes Void isn't just a hole in space. It's a hole in our understanding, a reminder that the universe reserves the right to surprise us. Whether it's a relic of unseen physics or a signpost to realms beyond our own, one thing is certain: the cosmos doesn't owe us symmetry. Sometimes it serves up emptiness on a scale so vast, it leaves us staring into the abyss, wondering what else we've missed. Einstein's theory of relativity gave us one of the most mind-bending truths about the universe: time isn't constant. It bends, stretches, and warps depending on gravity and speed. We see this every day with GPS satellites. Their atomic clocks tick ever so slightly faster than those on Earth, a phenomenon called time dilation. Without constant adjustments, your phone's navigation would be off by miles within minutes. But what if these distortions aren't just predictable quirks of physics? What if time itself has hidden wrinkles we've yet to understand? Take the infamous Pioneer Anomaly, the unexplained deceleration of NASA Pioneer probes. While most of the mystery was solved by accounting for heat radiation, some anomalies in the data lingered. One tantalizing hypothesis: minute, unaccounted for variations in the flow of time itself. If gravity or motion can warp time, could other forces, dark energy, quantum fluctuations, or even undiscovered dimensions, tweak it further? Then there's the curious case of flyby anomalies. When spacecraft like Galileo or Rosetta swing past Earth for a gravity boost, their speeds sometimes shift in ways Newton's laws can't fully explain. Some scientists speculate these discrepancies might hint at subtle, localized time warps like invisible currents in the fabric of space-time, nudging the probes off course. Even more bizarre are lab experiments with supercooled atoms. In certain quantum states, particles seem to feel time differently, as if the rules of causality loosen at microscopic scales. But the real enigma lies in deep space. Pulsars, the universe's most precise clocks, sometimes skip a beat. These ultra-dense neutron stars spin with such regularity that their radio pulses rival atomic clocks. Yet occasionally their rhythms stutter. Glitches in rotation could be caused by internal quakes. But what if some of these hiccups aren't mechanical at all? Could they be signatures of space-time itself flickering, like a faulty metronome in the cosmic symphony? The unsettling truth is this: time may not be the steady, uniform river we imagine. It might have rapids, eddies, even hidden whirlpools where the rules change. Every unexplained tick of a clock, every anomalous spacecraft trajectory whispers the same question: are we missing a piece of time's puzzle? Until we find it, the universe's clockwork remains just a little out of sync. In October 2017, astronomers spotted something streaking through our solar system that didn't belong, a visitor from another star. Named Oumuamua, Hawaiian for scout, this mysterious object was the first confirmed interstellar interloper ever detected. But what made it unforgettable wasn't just its origin, it was the way it defied every expectation. For starters, Oumuamua didn't look like any known comet or asteroid. Most solar system objects are roughly spherical or lumpy, shaped by eons of collisions and gravity. Oumuamua, though, was elongated. Some estimates suggested 10 times longer than it was wide, like a cosmic cigar tumbling end over end. Then there was its motion. As it slingshotted past the sun, it accelerated in ways that couldn't be explained by gravity alone. Comets usually get a speed boost from evaporating ice, which creates a visible tail. But Oumuamua had no tail, no coma, no detectable outgassing at all. It was as if some unseen force were pushing it. Theories exploded. Maybe Oumuamua was a shard of a shattered planet, ejected from another star system in a violent collision. Or perhaps it was a rare hydrogen iceberg, a hypothetical object that could accelerate silently as sunlight vaporized its frozen hydrogen surface. But the most provocative idea came from Harvard astrophysicist Avi Loeb, who suggested Oumuamua might be artificial, a light sail or probe sent by an alien civilization. Its unusual shape, absence of outgassing, and sudden acceleration all fit the profile of a designed object, he argued, one built to surf the cosmos on starlight. Skeptics fired back. If Oumuamua was a light sail, where were the radio signals? Why no other signs of technology? Others pointed to more mundane explanations, like the release of trapped molecular hydrogen, a process that wouldn't leave a visible trail but could explain the acceleration. Later studies even proposed Oumuamua might be a chunk of nitrogen ice sheared off a Pluto-like exoplanet, though no such objects had ever been observed. The truth we may never know. By the time Oumuamua was spotted, it was already racing out of the solar system, too faint and distant for further study. It left behind a trail of questions, challenging our assumptions about what lurks between the stars. Was it a natural oddity, a fragment of some alien world we've yet to understand? Or something far more extraordinary, a relic of intelligence, drifting through the void on a journey we can only guess at? What makes Oumuamua so haunting isn't just the mystery of its identity, but what it represents, the possibility that the universe is teeming with objects we've barely begun to imagine. It's a reminder that the cosmos doesn't play by our rules, and that sometimes the most profound discoveries come in forms we never saw coming. We think we know what the universe is made of: atoms, stars, galaxies, the stuff we can see and touch. But here's the cosmic twist: half of it is missing. Not dark matter, not dark energy, but ordinary matter. the protons and neutrons that build planets and people. Scientists call this the missing baryon problem, and it's one of the most embarrassing gaps in modern astrophysics. Baryons are the building blocks of normal matter, everything from your body to the farthest quasar. Based on observations of the early universe, like the cosmic microwave background, we can calculate exactly how much baryonic matter should exist. Yet when astronomers tally up all the visible stars, gas, and dust, nearly half of it simply isn't there. It's like doing an inventory of your house and realizing half your furniture has vanished without a trace. So where is it hiding? The leading theory points to the cosmic web, the vast, invisible scaffolding of filaments that connect galaxies across the universe. These threads, made of superheated gas, are so diffuse they're nearly impossible to detect with traditional telescopes. Imagine trying to spot a single light bulb in a foggy city. That's the challenge astronomers face. But in 2017, two independent teams finally caught a glimpse of this elusive matter. Using distortions in the cosmic microwave background as a backlight, they detected the faint imprint of oxygen ions in these filaments, confirming that at least some of the missing baryons are lurking there, woven into the fabric of the cosmos. But the mystery deepens. Even with these detections, the numbers still don't fully add up. Why is this gas so hard to find? Part of the problem is temperature. The missing baryons aren't cold enough to glow like stars or dense enough to block light like dust. Instead, they exist in a lukewarm limbo, emitting only faint X-rays that slip through our detectors like whispers in a storm. Another clue comes from quasars, whose light sometimes shows absorption lines, telltale signs of intervening gas clouds. Yet these clouds account for only a fraction of the total. The most unsettling possibility: we might be missing entire reservoirs of matter, hidden in forms we don't yet recognize. Could there be vast, undetectable structures, cosmic shadows, that don't interact with light the way we expect? Or is the universe playing tricks with gravity itself, redistributing matter in ways our models can't predict? Every new observation peels back another layer, revealing just how much we still don't understand about the ordinary stuff that makes up our reality. The missing baryon problem isn't just a scientific hiccup, it's a humbling reminder that even the familiar can defy explanation. We're surrounded by the universe's matter, woven into its very fabric, and yet half of it remains a ghost, slipping through our fingers like cosmic smoke. Until we solve this puzzle, we're left staring at the night sky, wondering what else might be hiding in plain sight. Tabby's star may be the most famous cosmic oddball, but it's far from alone in its strange behavior. Across the galaxy, astronomers have spotted other stars flickering in ways that defy explanation. Light curves so bizarre, they've sparked debates about everything from undiscovered physics to alien megastructures. Take Epoch 2444935.8.5, a star observed by NASA Kepler Space Telescope in 2018. Like Tabby's star, it showed erratic, asymmetrical dips in brightness, but this time the dimming wasn't gradual. The star's light dropped a staggering 80% in just one day, as if a colossal shadow had swept across its surface. Then, just as suddenly, it brightened again. No known natural phenomenon, comets, swarms, dust clouds, or even rogue planets, can explain such extreme, rapid changes. Then there's VVVWIT07, a giant star in the Milky Way that dimmed by 97% over several years before slowly recovering. Imagine our sun shrinking to the brightness of a full moon for a decade, then flickering back on without warning. The leading theory: an enormous, opaque disk, possibly a warped protoplanetary ring or debris field, orbiting the star edge-on, eclipsing it in slow motion. But here's the catch: the disk would need to be hundreds of times wider than Saturn's rings, stretching farther than the distance from Earth to the Sun. Nature rarely produces structures so perfectly aligned, leaving astronomers wondering if they're seeing something entirely new. What ties these mysteries together isn't just their strangeness, it's the way they force us to rethink the boundaries of known astrophysics. Some researchers argue these light curves could reveal exotic stellar phenomena, hyperactive magnetic fields, unseen companion stars, or even failed black holes lurking in binary systems. Others, like astronomer Jason Wright, suggest we might be glimpsing the fingerprints of advanced civilizations. Imagine a Type II civilization on the Kardashev scale, one capable of harnessing the energy of its entire star. Such a society might construct vast arrays of orbiting solar collectors, or even planet-sized megastructures like Dyson swarms, which would block starlight in irregular geometric patterns. The problem, of course, is evidence. Extraordinary claims require extraordinary proof, and so far, no radio signals or technosignatures have been detected from these stars. But the absence of answers is just as compelling. Every unexplained light curve is a cosmic riddle, a challenge to our understanding of how stars, and perhaps civilizations, evolve. As telescopes grow more sensitive and AI sifts through mountains of data, one thing is certain: the universe has more surprises in store. Whether these flickering stars are natural wonders or something more profound, they remind us that the cosmos is still writing its own rules, and we're just beginning to read them. For nearly a century, the Hubble constant, the rate at which the universe expands, has been astronomy's North Star, guiding our understanding of cosmic evolution. But in the last decade, that star has begun to flicker. Two of science's most trusted methods for measuring this fundamental number now disagree by a hair-raising margin, creating what astronomers call the Hubble tension. On one side, we have the gold standard, observations of the cosmic microwave background, the faint afterglow of the Big Bang. These measurements, painstakingly compiled by the Planck satellite, suggest the universe expands at about 67 kilometers per second per megaparsec. On the other side, measurements of nearby stars and supernova, celestial yardsticks known as Cepheid variables, point to a noticeably faster rate, 73. That 6-kilometer gap might seem trivial, but in the precise world of cosmology, it's a chasm. Either we're missing something fundamental about how the universe works, or our tools are betraying us in ways we don't yet understand. The implications are staggering. If the Cepheid measurements hold, it means the universe is expanding nearly 10% faster than our best models predict, a discrepancy that could unravel decades of cosmological theory. Some researchers argue this might hint at exotic new physics, like an unseen form of dark energy that grew stronger over time, or even an extra, dark particle species subtly tweaking the universe's expansion in its infancy. Others propose more radical ideas. Perhaps gravity itself behaves differently on cosmic scales, or the fabric of space-time contains hidden wrinkles that distort our measurements. Then there's the unsettling possibility that one or both of these methods harbors a subtle, undetected flaw. Could Cepheid variables, the very stars we've relied on for a century to gauge cosmic distances, be less reliable than we thought? Or does the cosmic microwave background, that pristine snapshot of the early universe, hide complexities we've yet to unravel? What makes the Hubble tension so compelling isn't just the scientific stakes, it's the way it exposes the limits of human knowledge. Here we are, armed with telescopes that can peer back to the universe's first light, yet we can't agree on something as basic as how fast space is stretching. Every new observation deepens the mystery. In 2019, measurements of gravitational waves from colliding neutron stars added a third data point, landing uncomfortably between the two camps. Meanwhile, independent studies using red giant stars or quasars keep muddying the waters, some siding with Planck, others with the Cepheids. The universe, it seems, is refusing to give us a straight answer. At its core, the Hubble tension is more than a technical disagreement, it's a cosmic wake-up call. For all our progress, the universe still holds cards close to its chest. Whether the solution lies in undiscovered physics, hidden measurement biases, or something even stranger, one thing is clear. The cosmos has a habit of humbling us just when we think we've got it figured out. Until we crack this puzzle, every calculation, every model, every theory about the fate of the universe carries an asterisk, a silent acknowledgement that somewhere, in the vast expanse of the unknown, we might have taken a wrong turn. And that's what makes science so thrilling, not the answers we have, but the mysteries that keep us searching. Mars should be the perfect candidate for life beyond Earth, a neighboring world with a history of flowing water, a thick atmosphere in its past, and even organic molecules detected on its surface. Yet after decades of robotic explorers scouring its deserts, drilling into its rocks, and sniffing its thin air, the red planet remains eerily silent. No fossils, no microbial hitchhikers, not even a whisper of metabolic activity. This cosmic quiet has left scientists grappling with a haunting question. Is Mars truly barren, or are we just looking in all the wrong places? Consider the clues that once made Mars seem like a prime habitat for life. Satellite images reveal ancient river valleys and lake beds, proof that liquid water once pooled on its surface. The Curiosity rover found complex organic molecules, the building blocks of life, embedded in billion-year-old mudstones. Even today, methane sporadically spikes in the Martian atmosphere, a gas often tied to biological activity on Earth. Yet every follow-up experiment has come up empty. The Viking landers of the 1970s conducted the first ever life detection tests on another planet, mixing Martian soil with nutrients to see if microbes would metabolize them. The results were baffling. Chemical reactions occurred, but none conclusively pointed to biology. Decades later, newer rovers like Perseverance hunt for fossilized microbes, but so far, the rocks tell only a story of geology, not life. The frustration lies in the paradox. Mars had all the ingredients for life: water, energy sources, and organic material. So where is everyone? One possibility is that life did arise, but vanished billions of years ago as the planet dried up and lost its protective magnetic field, leaving its surface bathed in sterilizing radiation. Another theory suggests life might still exist, but in niches we've yet to explore, deep underground aquifers shielded from the harsh surface, or in briny layers beneath the polar ice caps. Imagine extremophile bacteria on Earth, thriving in acidic hot springs or buried kilometers below Antarctica. If life clings to such hostile places here, why not beneath Mars's rusty soil? Then there's the unsettling idea that we might be blind to Martian life because it's fundamentally different from what we recognize. Our tools are calibrated for Earth like biology, DNA, cell membranes, water-based chemistry. But what if Martian microbes use alternative biochemistries, like silicon instead of carbon, or solvents other than water? The Viking experiments assumed life would metabolize nutrients the way Earth organisms do. If Martian biology operates on a different rulebook, our tests might have missed it entirely. The silence of Mars isn't just a scientific puzzle, it's a mirror. It forces us to confront how little we truly know about the boundaries of life. Every empty drill sample, every inconclusive gas reading, whispers the same humbling truth: the universe doesn't owe us neighbors. Whether Mars is a graveyard of lost biology or a world that never sparked with life at all, its quiet stretches before us like an unsolved riddle, daring the next generation of explorers to listen harder, dig deeper, and question everything we think we know about what it means to be alive. Deep in the heart of our galaxy, something is generating an avalanche of energy, an invisible firestorm of gamma rays that shouldn't exist. Known as the galactic center excess, this mysterious surge of high-energy photons has baffled astronomers since its discovery in 2009. The Milky Way's core should be crowded with predictable gamma-ray sources, pulsars, supernova remnants, the supermassive black hole Sagittarius, a star. But when scientists subtracted all these known contributors from Fermi Space Telescope data, they were left with a glaring surplus, a diffuse, glowing halo of gamma rays radiating from the galactic center with no obvious explanation. Theories split into two camps, each more intriguing than the last. The first points to dark matter, the elusive substance making up 85% of the universe's mass. If dark matter particles are their own antiparticles, they might annihilate upon collision, releasing gamma rays as a byproduct. The galactic center, with its immense gravitational pull, would naturally concentrate these particles, creating a detectable signal. It's a tantalizing idea, the first potential glimpse of dark matter's hidden nature, but there's a catch. The energy signature doesn't perfectly match predictions. If this is dark matter, it's behaving in ways our models never anticipated. The second theory suggests a cosmic crowd of pulsars, the dense, spinning corpses of dead stars. These stellar lighthouses emit gamma rays as their powerful magnetic fields whip charged particles to near light speeds. Thousands of unresolved pulsars in the galactic bulge could, in theory, combine to mimic the excess. Yet searches for these objects have come up short. Where are the telltale radio pulses or X-ray counterparts we'd expect to see? Either we're missing something fundamental about pulsar populations, or nature is playing a trick on us. What makes this mystery so compelling isn't just the unanswered questions, it's the stakes. If the excess stems from dark matter, it could revolutionize physics, offering the first direct clue to a substance that shaped the cosmos since the Big Bang. If pulsars are the culprit, it means our galaxy's core harbors a hidden ecosystem of stellar remnants we've barely begun to map. And then there's the wild card. Could this signal be something entirely new, a cosmic process we've yet to imagine? Every new observation adds layers to the puzzle. Some studies suggest the excess isn't perfectly spherical, as dark matter models predict, but slightly elongated, hinting at an alternative origin. Others argue the gamma-ray spectrum varies in ways that defy simple explanations. The truth might lie in a combination of factors, or in physics we've yet to uncover. One thing's certain, the galactic center isn't just a place of supermassive black holes and swirling stars. It's a cosmic laboratory, broadcasting secrets we're only beginning to decode, and the more we listen, the stranger the universe becomes. The moon hangs in our night sky like a silent sentinel, a familiar companion that seems to hold no secrets. But beneath its cratered surface lies a mystery that defies everything we know about planetary magnetism. Rock samples brought back by the Apollo missions revealed something astonishing. The moon once had a magnetic field, potentially even stronger than Earth's today. Here's the puzzle: with a core just 1% the size of Earth's, the moon shouldn't have been capable of generating such a field in the first place. For a magnetic field to exist, a planet needs a churning, molten metal core acting like a dynamo. Think of Earth spinning inner core generating our protective magnetic shield. But the moon's core is small, cool, and mostly solid. So how did it pull off this cosmic magic trick? One theory suggests the moon's early dynamo was powered by an entirely different mechanism. In its youth, the moon orbited much closer to Earth, and the gravitational tug of war between the two bodies might have stirred its core like a spoon in molten metal. This mechanical stirring could have jump-started a temporary magnetic field, fueled not by internal heat but by sheer brute force of motion. Then there's the impact hypothesis. The moon's surface is scarred by ancient collisions, some so violent they could have reshaped its interior. A massive strike might have disrupted the core, sending shockwaves that briefly liquefied it and kick-started a magnetic dynamo. Imagine hitting a gong so hard the vibrations ripple through to its core. That's the kind of energy we're talking about. But if that's the case, why did the field persist for hundreds of millions of years after these impacts faded? The plot thickens with the discovery of magnetized lunar rocks dating back 3.5 billion years, long after the moon's core should have cooled beyond dynamo activity. Some researchers propose a radical solution: crystallization-driven convection. As the moon's core slowly solidified, lighter elements like sulfur might have risen, creating currents that sustained the magnetic field far longer than expected. It's like a candle wick burning steadily as the wax melts away. But the most tantalizing possibility: the moon's field wasn't homegrown at all. Earth's own magnetic field might have extended outward, enveloping the moon in a protective bubble during their close orbital dance. If true, the moon's rocks could be preserving an ancient snapshot of Earth's magnetism, a ghostly echo of our planet's past. The moon's magnetic mystery isn't just a lunar curiosity. It's a window into the chaotic early solar system, where planetary bodies evolved under conditions we can barely replicate in models. Every new moon rock analyzed, every simulation run, brings us closer to understanding how something so small could wield such cosmic influence. Until then, the moon keeps its secrets locked in silent stone, reminding us that even our closest celestial neighbor still has stories left to tell. Imagine the universe as a grand cosmic play where everything we see, stars, planets, galaxies, are merely the actors on stage. But behind the scenes, hidden in the shadows, lies the true director, dark matter. This invisible substance makes up 27% of the cosmos, outweighing all ordinary matter by a factor of 5 to 1. Yet despite its overwhelming presence, it refuses to interact with light, leaving us to trace its existence only through the ghostly fingerprints it leaves on the visible universe. The story begins in the 1930s when astronomer Fritz Zwicky noticed something peculiar about the Coma cluster of galaxies. The visible mass of these galaxies couldn't account for their gravitational pull. They were moving too fast, as if held together by some unseen anchor. He called this missing mass Dunkel Materie, dark matter, a term that would haunt cosmology for nearly a century. Decades later, Vera Rubin's observations of spinning galaxies confirmed the enigma. Stars at the edges of galaxies orbited just as fast as those near the center, defying Newton's laws unless some invisible mass was holding them in place. But what is dark matter? The leading candidate is WIMP, weakly interacting massive particles, hypothetical subatomic particles that pass through ordinary matter like ghosts through walls. Billions might be streaming through your body right now, leaving no trace. Experiments like the Large Underground Xenon Detector hunt for these elusive particles, waiting for the rare moment one bumps into an atom. So far, silence. Other theories propose actions, ultra-light particles with a faint magnetic signature, or even primordial black holes forged in the Big Bang's first seconds. The frustration lies in the paradox. Dark matter's gravitational influence is undeniable. It sculpts the cosmic web, bends light in gravitational lenses, and dictates where galaxies form. Yet it remains aloof, refusing to emit, absorb, or reflect light. It's like trying to study a shadow by shining a flashlight. The harder we look, the more it slips away. Perhaps the most unsettling possibility is that dark matter isn't a single thing at all, but a menagerie of exotic particles and forces operating outside our current physics. Or worse, what if we've misunderstood gravity entirely? Modified Newtonian dynamics, or MUND, suggests that on cosmic scales, gravity might behave differently, negating the need for dark matter. But MUND struggles to explain all observations, leaving most scientists convinced that something unseen is out there. Every telescope, every particle detector, every supercomputer simulation brings us closer to the truth, or deeper into the mystery. Dark matter isn't just a missing piece of the puzzle. It's a reminder that most of the universe is written in ink we can't yet read. Until we crack its code, we're left groping in the dark, mapping the cosmos by the shape of its absences. The universe isn't just a random scattering of galaxies, it's an intricate tapestry, a vast cosmic web where galaxies cluster along sprawling filaments like beads on an invisible string. These filaments stretch across billions of light years, connecting massive nodes where galaxy clusters collide, while leaving behind yawning voids of near nothingness. But how did this delicate, spider-like structure emerge from the chaos of the Big Bang? The answer lies in the subtle tug of war between dark matter's invisible scaffolding and the gravitational dance of ordinary matter, a process so precise it borders on artistry. Rewind to the universe's infancy, a seething plasma of particles and energy. Tiny quantum fluctuations, random ripples in density, were baked into the fabric of space-time during the universe's explosive first moments. As the cosmos expanded and cooled, these minuscule wrinkles grew under gravity's relentless pull. Dark matter, unaffected by the pressure of light or heat, began collapsing first, forming an invisible skeleton of dense knots and threads. Ordinary matter, slowed by radiation's push, eventually followed, flowing into these gravitational troughs like water filling riverbeds. Over billions of years, this interplay sculpted the universe into the filamentary web we see today. Yet the details remain tantalizingly fuzzy. Simulations like the Millennium run supercomputer models tracking trillions of particles, recreate the cosmic web with stunning accuracy, but they hinge on assumptions about dark matter's behavior. What if dark matter isn't as cold or collisionless as we think? Alternative theories like warm dark matter or self-interacting dark matter predict subtly different web structures with thinner filaments or fewer small-scale clumps. Then there's dark energy, the mysterious force accelerating the universe's expansion, which may have subtly warped the web's growth over time. Even more intriguing are the web's missing filaments. In 2014, astronomers stumbled upon a strand of intergalactic gas in the distant universe, a thread of the cosmic web finally made visible. But many predicted filaments remain elusive, their diffuse gas too faint to detect. Some may hide in plain sight, disguised as the missing baryons we've yet to account for. Others might be woven from exotic particles we've yet to discover. The cosmic web isn't just a relic of the past, it's a living structure. Even now, galaxies are funneled along filaments like cosmic highways, drawn toward the web's dense nodes in a slow-motion migration that will continue for billions of years. These nodes, the universe's great metropolises, host violent collisions of galaxy clusters, while the voids between them grow ever emptier as dark energy stretches space-time apart. What's truly humbling is how much we still can't see. The web's finest threads, the faintest tendrils of gas and dark matter, lie beyond our current telescope's grasp. Future observatories like the James Webb Space Telescope or next-generation radio arrays may finally illuminate these hidden strands, revealing the full blueprint of the universe's architecture. Until then, the cosmic web remains both a triumph of cosmological theory and a reminder of how much lies hidden in the spaces between the light. Saturn, the jewel of our solar system, is famous for its dazzling rings, but hidden in the swirling clouds at its north pole lies something far stranger. A colossal hurricane, large enough to swallow Earth whole, rages with winds screaming at 300 miles per hour. Yet this isn't just any storm. For reasons that defy all known atmospheric physics, this tempest has locked itself into a near-perfect hexagon, a six-sided geometric freak of nature that's persisted for at least 4 decades. No other planet, not even Jupiter with its great red spot, exhibits weather so stubbornly symmetrical. The hexagon was first glimpsed by NASA Voyager probes in the 1980s, dismissed by some as a camera artifact. But when the Cassini spacecraft arrived in 2004, there it was unchanged, a razor-sharp polygon etched into Saturn's atmosphere like a cosmic etch-a-sketch drawing. Each side stretches nearly 9,000 miles, with jet streams along its edges moving at different speeds, creating a wall of wind that somehow holds the shape intact. On Earth, storms dissolve into chaos within days. This one has outlasted generations of scientists. So what's keeping the hexagon so eerily precise? One leading theory points to deep-rooted atmospheric layering. Saturn, a gas giant, lacks a solid surface, but its atmosphere may stack like fluids of different densities in a laboratory experiment. Computer simulations show that when fluids with varying speeds interact in a rotating system, geometric patterns can emerge, but never naturally at this scale or stability. Another idea suggests standing waves, like vibrations in a giant cosmic bell, could be sculpting the storm's edges, yet these explanations struggle to account for the hexagon's longevity or its crisp angles. Then there's the wild card polar vortices. Earth has them too, but Saturn's version is a churning maelstrom pinned directly at the hexagon's center, possibly acting like an anchor. Some researchers speculate this vortex generates acoustic waves that resonate outward, organizing the chaos into a rigid structure. It's as if the storm is trapped in a self-reinforcing feedback loop, a whirlpool caught in an invisible cage of its own making. The hexagon's most haunting quality isn't just its shape, it's the way it mocks our understanding of fluid dynamics. Nature abhors straight lines, yet here's a tempest that's all angles and edges, a storm that plays by rules we've yet to decipher. Every new observation peels back another layer, revealing hints of smaller, nested hexagons within the main structure or subtle color shifts as Saturn's seasons change. But the core mystery remains. In a universe of randomness, why does this one patch of sky cling so fiercely to order? Perhaps the answer lies deeper than the clouds. Saturn's hexagon might be a Rosetta Stone for planetary atmospheres, a clue to hidden forces shaping weather on gas giants across the cosmos. Or maybe it's a cosmic coincidence, a fleeting alignment of conditions that will one day unravel as silently as it formed. Until then, it spins on a six-sided enigma, whispering that even in the chaos of space, there's room for geometry we can't yet explain. Venus, our so-called twin planet, is a world of extremes, crushing atmospheric pressure, scorching temperatures, and acid rain that evaporates before it hits the ground. But perhaps its strangest feature spins silently above its south pole, a colossal double vortex, a pair of intertwined hurricanes locked in an endless dance. This atmospheric enigma, first spotted by the European Space Agency's Venus Express orbiter in 2006, defies every expectation of how planetary weather should behave. Unlike Earth's transient storms, this vortex has persisted for decades, possibly centuries, its twin funnels rotating like interlocking gears in a machine no one built. What makes this vortex so baffling isn't just its longevity, it's the way it flips textbook meteorology on its head. On Earth, hurricanes feed off warm ocean water, dissipating once they hit land or cooler seas. Venus has no oceans, no liquid water at all. Its hellish surface bakes at nearly 900 degrees Fahrenheit, yet its upper atmosphere, where the vortex churns, is oddly temperate, with winds screaming at 200 miles per hour. Even more perplexing is the vortex's double structure. Most polar vortices, like Earth's Arctic whirlwinds, are single, chaotic systems. Venus's version is a precise, symmetrical duo, as if an invisible hand carved it from the clouds. Scientists have scrambled for explanations. One theory points to Venus's super-rotation. Its atmosphere whips around the planet 60 times faster than the surface rotates, a phenomenon unmatched in the solar system. This creates colossal shear forces, twisting the polar winds into a stable, self-reinforcing spiral. Others suggest the vortex is a drain for the planet's global circulation, where air rushing poleward from the equator sinks in a violent, turbulent cascade. But why two eyes instead of one? Some computer simulations hint that Venus's extreme axial tilt, or lack thereof, might split the vortex into twins, like water swirling around dual drains in a bathtub. Then there's the wild card, chemistry. Venus's atmosphere is a toxic cocktail of sulfuric acid and carbon dioxide, with mysterious dark streaks absorbing ultraviolet light. Could unknown chemical reactions be fueling the vortex's stability? Or does the answer lie deeper in the planet's volcanic activity? Recent studies suggest massive eruptions might pump enough heat and gas into the atmosphere to sustain the vortex, turning it into a planetary-scale pressure valve. The most haunting possibility: we're seeing a shadow of Venus's lost past. Billions of years ago, before its runaway greenhouse effect turned it into a furnace, Venus might have had oceans and a climate not unlike Earth. Could the vortex be a relic of that ancient system, a ghostly imprint of weather patterns that once rained water instead of acid? Every probe sent to Venus peels back another layer, but the vortex remains a riddle, a swirling reminder that even our closest planetary neighbor hides secrets we've only begun to unravel. On the morning of June 30th, 1908, deep in the remote Siberian wilderness, a blinding fireball tore across the sky, so bright it cast shadows hundreds of miles away. Minutes later, an explosion ripped through the air with the force of 12 million tons of TNT, flattening 800 square miles of forest like matchsticks. Trees were snapped in half, their trunks radiating outward from ground zero in a haunting butterfly-shaped pattern. Windows shattered 600 miles away. Seismic waves circled the globe twice, and yet, when scientists finally reached the epicenter years later, they found no crater, no fragments, no smoking gun, just silence where the Earth itself seemed to have been punched by an invisible fist. This is the Tunguska event, one of the most violent cosmic encounters in recorded history, and to this day we still don't know exactly what caused it. The leading theory points to a stony meteor or comet fragment, roughly 60 meters wide, that detonated 5 to 10 kilometers above the surface. The heat of atmospheric entry would have vaporized it instantly, creating a shockwave powerful enough to level forests but leaving no trace. Yet even this explanation has holes. Comets made of ice and dust should have left telltale chemical traces in the soil. Meteors often scatter debris, but searchers turned up no significant fragments. The lack of a crater suggests an airburst, but the energy required defies most known near-Earth objects. Then there are the stranger possibilities. Could it have been a chunk of antimatter, annihilating itself in a flash of gamma rays? Unlikely. Such an event would leave radioactive isotopes, none of which were found. Some have even speculated about microscopic black holes or alien spacecraft, though these ideas veer into science fiction without evidence. One tantalizing alternative: a massive methane explosion from beneath the Siberian permafrost, though this fails to explain the fiery streak witnessed across the sky. What makes Tunguska so unsettling isn't just the mystery, it's the timing. Had the object arrived just 4 hours later, it would have struck St. Petersburg, wiping out a city of millions. Instead, it chose one of the most uninhabited places on Earth, as if the universe were giving us a warning shot. Today, smaller airbursts occur every few decades, like the Chelyabinsk meteor of 2013. But Tunguska-scale events are rarer, striking every few centuries. The next one could happen tomorrow, or 1,000 years from now. The Tunguska event lingers as a cosmic riddle, a reminder of how fragile our place in the universe truly is. It's not just a historical curiosity, it's a wake-up call. With no crater to mark it, no culprit to blame, it forces us to confront how much we still don't see, and how little it would take to change everything. Imagine stepping outside on a clear, moonless night, hours before dawn or after sunset, and spotting a faint, ghostly pyramid of light rising from the horizon. This ethereal glow isn't the Milky Way or a trick of the eye. It's the zodiacal light, a cosmic spectacle caused by sunlight scattering off trillions of dust particles drifting along the same plane as the solar system. But here's the twist: this dust shouldn't exist in such abundance, and its peculiar distribution has astronomers scratching their heads. For centuries, the zodiacal light was thought to be a simple phenomenon, the leftover debris from asteroid collisions and comet tails, ground into fine powder over billions of years. Yet modern observations reveal a glaring mismatch. The dust is too evenly spread, too densely concentrated, and far too persistent for known sources to explain. Asteroids and comets do contribute, but their debris tends to clump or disperse over time, leaving gaps the zodiacal light doesn't show. Even more puzzling, the dust extends far beyond the inner solar system, forming a smooth, luminous band that defies the chaotic origins we'd expect. One leading theory points to Mars as a hidden culprit. The planet's thin atmosphere and frequent dust storms might be launching particles into space, where solar radiation pushes them into the ecliptic plane. Another idea involves Jupiter's gravity herding interstellar dust into our solar system's orbital highway, but neither fully accounts for the light's sheer intensity or its eerie symmetry. Some researchers speculate about a more exotic source: collisions between distant objects in the Kuiper belt, or even a long-vanished planetesimal belt whose remnants still haunt the inner solar system. Then there's the wild card, the dust's bizarre thermal properties. Observations by spacecraft like NASA's Juno probe reveal the particles are far more reflective and evenly sized than predicted, almost as if they've been polished or processed by some unseen force. Could electrostatic levitation or solar wind be sculpting them into this unnatural uniformity? Or does the answer lie deeper, in a previously overlooked reservoir of dust replenished by an unknown cosmic mechanism? The zodiacal light isn't just a celestial curiosity, it's a mirror reflecting our incomplete understanding of the solar system's hidden architecture. Every new mission, from orbital telescopes to deep space probes, peels back another layer of the mystery. Until we solve it, this soft glow remains a silent reminder. Even in our own cosmic backyard, the simplest phenomena can harbor the most profound secrets. High above our heads, the universe is firing bullets, cosmic bullets so powerful, they carry more energy than a major league fastball packed into a single subatomic particle. These are ultra-high-energy cosmic rays, mysterious messengers from the depths of space that slam into Earth's atmosphere with forces exceeding 100 million times what the Large Hadron Collider can produce. Imagine a single proton, a speck so small it's invisible to every microscope, hurtling through space with enough punch to knock over a bowling ball. That's the scale of this cosmic absurdity, and it defies everything we know about how the universe accelerates particles. The mystery begins with their origin. Cosmic rays are common charged particles zipping through space, but most are low-energy scraps, the fallout of supernova or solar flares. The ultra-high-energy variety are something else entirely. Detected by observatories like the Pierre Auger Array in Argentina, these rare events strike Earth's atmosphere roughly once per square kilometer per century, exploding into showers of secondary particles that rain down over miles. Their energy levels are so extreme they shouldn't exist. According to physics, particles this energetic should lose steam over long distances, sapped by collisions with the cosmic microwave background radiation, a phenomenon called the Greisen-Zatzepin-Kuzmin cutoff. Yet here they are, arriving with enough juice to make physicists question whether our models of the universe are missing a page. So what cosmic monster could be launching these particles? One candidate is active galactic nuclei, supermassive black holes at the hearts of galaxies, devouring matter and spewing jets of plasma at near light speed. These cosmic accelerators could theoretically boost particles to such absurd energies, but there's a catch. We haven't found a single black hole powerful or close enough to explain the rays we've detected. Another possibility involves gamma-ray bursts, the universe's most violent explosions, capable of outshining entire galaxies for seconds. Yet these events are fleeting, and ultra-high-energy cosmic rays seem to arrive from all directions, not just burst hotspots. Then there's the wild card topological defects. In the chaotic aftermath of the Big Bang, space-time itself might have knotted into flaws like cracks in cooling glass. If these defects unraveled, they could release bursts of energy capable of flinging particles across the cosmos. It's a fringe idea, but when conventional physics fails, even the strangest theories get a hearing. The real frustration lies in the clues these particles refuse to give. Unlike light or radio waves, cosmic rays are scrambled by magnetic fields during their journey, making it nearly impossible to trace their paths back to a source. It's like trying to find a sniper by studying the bullet's wobble mid-flight. Every detection is a cipher, a message from the cosmos written in a code we're still learning to read. What makes ultra-high-energy cosmic rays so thrilling isn't just their power. It's the way they force us to confront the limits of our knowledge. They're cosmic outliers, exceptions to rules we thought were ironclad. Every time one streaks through our atmosphere, it's a reminder. The universe has engines of destruction and creation we've yet to imagine, and they're firing blindly in the dark, daring us to understand. The universe isn't just expanding. It's accelerating, flying apart at ever-increasing speeds, as if some unseen hand were pressing down on the cosmic gas pedal. This startling discovery, made in the late 1990s by teams studying distant supernova, upended our understanding of cosmology and revealed the existence of a mysterious force we now call dark energy. Imagine tossing a ball into the air, only to watch it shoot away faster and faster instead of falling back to Earth. That's the counterintuitive reality we're facing, and it hints at a cosmic puzzle so profound, it might rewrite the laws of physics as we know them. Dark energy isn't just another mystery, it's the dominant force in the universe, making up a staggering 68% of all the energy in the cosmos. Yet we can't see it, touch it, or even detect it directly. We only know it's there by its gravitational fingerprint, the way it stretches space-time itself, pushing galaxies apart with a force that grows stronger as the universe expands. The simplest explanation, proposed by Einstein himself, is the cosmological constant, a property of empty space that exerts negative pressure, like a cosmic spring that never winds down. But here's the catch. When physicists calculate how strong this effect should be based on quantum theory, their predictions overshoot reality by a factor of 10 to the power of 120. That's not just a rounding error, It's the worst mismatch in the history of science. Alternative theories abound. Some suggest dark energy isn't constant but evolves over time, a hypothetical field called quintessence that changes strength as the universe ages. Others propose even wilder ideas, like hidden extra dimensions leaking gravitational influence into our universe, or a flaw in Einstein's theory of gravity that only becomes apparent on cosmic scales. Then there's the radical notion that dark energy isn't a force at all, but an illusion caused by our galaxy occupying a rare void in an otherwise clumpy cosmos, a cosmic mirage tricking us into seeing acceleration where none exists. The stakes couldn't be higher. If dark energy is real and continues unchecked, it could eventually tear apart everything from galaxy clusters to atoms themselves in a distant future called the Big Rip. Alternatively, if it weakens or reverses, the universe might collapse back into a fiery crunch. Or perhaps it's just the first hint of a deeper layer of reality, a shadow of physics we've yet to uncover. Every new telescope, from the James Webb Space Telescope to upcoming projects like the Euclid satellite, brings us closer to answers or deeper into the mystery. What makes dark energy so humbling isn't just our ignorance, it's the way it forces us to confront how little we truly grasp about the fabric of reality. We're like ants trying to comprehend the ocean, standing on the shore of a cosmos that's stranger, richer, and more mysterious than we ever imagined. Until we crack its code, dark energy remains the ultimate cosmic question mark, a silent force shaping the fate of everything we see and everything we are. Imagine waking up one day with all your memories intact, your first kiss, your childhood home, the smell of rain on pavement, only to realize none of it was real. Your body, your world, even the stars above you, are nothing more than a fleeting arrangement of atoms, a momentary flicker of order in an otherwise chaotic universe. This is the chilling premise of the Boltzmann brain paradox, a thought experiment so unsettling it makes you question whether anything you perceive is real at all. The paradox traces its roots to 19th century physicist Ludwig Boltzmann, who grappled with a fundamental question: why does our universe appear so orderly? According to thermodynamics, systems naturally progress from order to disorder, a principle called entropy. Yet here we are, surrounded by structure, from DNA's double helix to the intricate dance of galaxies. Boltzmann proposed a radical solution. Given enough time, random fluctuations in a chaotic universe could, by sheer chance, create pockets of order. Most would be fleeting, a gust of wind arranging leaves into a smiley face, or a cloud briefly resembling a dragon. But given infinite time, even the most improbable events become inevitable. Enter the Boltzmann brain, a self-aware consciousness that spontaneously forms from a random collision of particles, complete with false memories of a life that never existed. Here's where it gets unnerving. If Boltzmann brains are possible, they're statistically far more likely than an entire ordered universe like ours. Think of it this way. It's easier for randomness to assemble a single thinking brain for a split second than to craft a cosmos with billions of galaxies lasting billions of years. So why do we perceive ourselves as real beings in a real universe, rather as momentary glitches in the void? Some physicists argue this paradox undermines our entire understanding of reality. If the math suggests Boltzmann brains should outnumber real observers like us by an unimaginable margin, how can we trust that we're not one of them? Critics fight back with cosmology's heavy artillery. The inflationary model of the Big Bang suggests our universe began in an ultra-low entropy state, making its current orderliness a natural outcome, not a statistical fluke. Others point to quantum mechanics, where conscious observation might play a role in collapsing probability waves, anchoring reality in a way randomness can't mimic. Then there's the anthropic principle. We perceive a stable universe because only such a universe could produce observers capable of perceiving it. Boltzmann brains, by contrast, would dissolve as quickly as they form, leaving no one to ponder their existence. Yet the paradox lingers, a ghost in the machine of modern physics. It forces us to confront the limits of probability, the nature of consciousness, and the terrifying possibility that our most cherished truths might be cosmic illusions. Whether a philosophical curiosity or a genuine crisis for cosmology, the Boltzmann brain reminds us that in an infinite universe, even the impossible might be waiting its turn. From unexplained signals echoing across the cosmos to vast voids where galaxies refuse to gather, these 29 mysteries aren't just scientific curiosities, they're humbling reminders of how little we truly grasp about the universe. Every flickering star, every gravitational anomaly, every silent stretch of space whispers the same truth. Reality is far stranger than our boldest theories. The WOW signal taunts us with the possibility of contact we can't confirm. Dark matter shapes the cosmos while eluding our detection. The great attractor pulls entire galaxies towards something we can't see. These aren't gaps in knowledge, they're doorways to discoveries that could rewrite textbooks and redefine our place in the cosmos. What makes these enigmas so exhilarating isn't just their complexity, it's the way they force us to rethink the fundamentals. Take the Hubble tension, where the universe's expansion rate refuses to give a straight answer, or Saturn's Hexagon, a storm that laughs at our understanding of fluid dynamics. Even the humble moon, our closest celestial neighbor, hides a magnetic past that defies physics. Each puzzle is a testament to the universe's playful defiance, a cosmic game of hide and seek where the rules keep changing. But here's the beautiful part: every mystery is an invitation. The Fermi Paradox challenges us to consider whether we're alone or just not listening right. Tabby's star and its flickering kin dare us to imagine technologies beyond our own. The missing Baryon problem proves that half the universe's ordinary matter is still hiding in plain sight, waiting for a sharper tool, a brighter idea, a fresh pair of eyes. Science isn't about having all the answers, it's about having the courage to ask better questions. So as we stare up at the night sky, let's not just see the stars, let's see the riddles woven between them. Which of these cosmic conundrums sparks your curiosity the most? Is it the haunting silence where alien chatter should be, the eerie perfection of a storm that shouldn't exist? Or the unsettling thought that dark energy might one day tear the universe apart? Drop your thoughts in the comments below. I'd love to geek out over these mysteries with you. And if you're hungry for more mind-bending explorations of space's greatest secrets, hit that subscribe button and ring the notification bell. The universe isn't done surprising us, and neither are we. Together, let's keep chasing the unknown, one enigma at a time.